Okay, welcome everybody to PhotoTech Day 22. Today we have new Googler, Eric Gross, speaking to us about a wavefront analysis approach to lens aberrations. Eric, take it away.
So I'm going to be talking about some of the recent technological developments that, for the first time, let us go in and measure all the optical aberrations in a human eye, sort of in a real amount of time without hurting the person. Getting that information, I'll be talking about what we can do with it and potentially using that to make their vision even better. My background is in physics, but I sort of got into the eyeball business, and I have to tell you, eyeballs, it turns out, are really cool. They are amazing. I won't be talking too much about eyeballs, just about the optics of them, but a few fun facts. You know, your retina can perceive as much as a single photon striking it, which is pretty remarkable. The cornea itself, tissue in there, is the only living tissue in the human body that doesn't have a blood supply. It gets all its oxygen directly diffusing from the air. So if you lived in a nitrogen environment, your corneas would shrivel up and die eventually. It's cool, fantastic stuff. But we're going to be talking about the optics of it, the eye as a camera. And there are a few main pieces that are important. You know this thin side. Adjust the light a little more, and it's how you do accommodation. If you want to change your focus to read some muscles, pull that in or out, and gives you better focus. And then everything gets imaged on the retina, the back. So if you are looking at a point source of light, in this example, say a star, something far away, by the time the rays reach your eye, they're coming in pretty parallel. So that's sort of the assumption that I will start with in this talk. If everything goes right, they get focused through the surfaces, and you get a nice point at the end. Then your eye is called emmetropic. And I'll be using that word a few times. It means well-focused eye, well-proportioned, an eye with no problems. It's a theoretical type of eye, but we'll get into that later. If you are nearsighted, you have a myopic eye, right? The light comes in. The light focuses too strongly, comes to an image before it hits your retina, something like that. The Greek origin is the word squinty eye. Can anyone imagine why myopic is called squinty in Greek? Right, yeah, sure. Because people who are myopic tend to squint to see better. In fact, a lot of vision problems do it, but this is the most common. And it's fairly obvious why. When you look at that, many fewer rays are coming in, and so what was a big blur is now just kind of a small blur, and you can manage to go through the day. Myopia is the most common visual complaint that people have. Generally, there's nothing wrong with the cornea. Their eye itself is longer than average. So the image gets formed, there's nothing there to hit it, the light goes on, gets a little messed up. And in this case, too long is pretty relative.
So does squinting change the geometric optics at all, or just the aperture?
It does change the geometric optics, but in a small way, and it actually induces a little bit of astigmatism, kind of on the axis you would expect. So that's not too useful for you.
But it doesn't contribute to refocusing?
It does not contribute to refocusing.
It stops down the pupil, so if you do it with a camera, you get a more depth of field? Yeah. Same thing.
Exactly. There's been a lot of debate and research into what causes myopia. It generally starts between the ages of 5 and 10 and kind of develops up to some point and then stops getting worse. There seems to definitely be a genetic component. If your parents were nearsighted, there's a good chance you will be. And there's also a definite environmental trigger. There are some sort of studies of, for example, an Eskimo culture in which there were essentially no visual problems or myopic-related visual problems until public schools came in, introduced reading, and then you could watch the prevalence of glasses sort of track up with the ages as the kids came in. So there's both. Reading seems to be the problem. Case study. If you're not myopic, the chances are you're a little bit hyperopic. Most people who go through their life without wearing glasses, at least at first, are in fact a little bit farsighted. 1 or 2 diopters is pretty common. And generally, they don't really notice it until you start getting older. Your accommodation doesn't work as well. And all of a sudden, you can't use that accommodation to pull it in and focus it. Then people have to start wearing reading glasses. So that's the optics of the eye. how well do you see? We measure that with this chart. Everybody's familiar with that chart. It's 150 years old, which is
What chart?
which is pretty amazing. There you go. You're supposed to stand, well, first off, you put it at a standard size, not this giant projected one. You stand 20 feet away, and you essentially read down until you can't read anymore. And then you look at the number to the right, and that tells you what your visual acuity is. It's always presented in two numbers, 20/20. The first one is the 20 feet that you're standing away, and the second number is how far away a person with normal vision would have to stand to read it. So if you're at 20/20, that means you have pretty much normal vision. The big E on the top, and it's almost always an E for some reason, doesn't have to be, is generally the legally blind point. So people who cannot read that, even with correction, they're legally blind, are people who, so the 20/40, this is the point where you have to wear glasses if you're driving, according to the DMV. And in fact, the chart goes significantly lower, and there are people that can see all the way down to those smallest lines. This is usually 20/20, 2015, 2010, 28, something like that. And this is sort of used all throughout the world, and it's really old, but it turns out that up until now, it was about the best way we had, or maybe it still is, to measure how well someone can see. Does anybody know what they call 20/20 in France? Royale with cheese? No. 6/6. So they just put it into meters and go to the closest unit. So you have this basic model of the eye. People have been creating models for a long time. This is called the Goldstrand-Four surface model, and I don't remember when he was doing it, but something like 100 years ago. Sort of tracing by hand, describing all these surfaces as basic spheres or variations. Figure out the index of refraction. Here's a Zemax model. Some of you guys were talking about Zemax last time. It's a basic model of the eye. But the problem here is that it's a real gross oversimplification. And until recently, we haven't been able to do anything about that. The reason that it's an oversimplification is that even a pretty well-focused eye doesn't actually look like this. This is an exaggeration, of course, but it looks something like this. That's not a nice, smooth lens surface. You have little imperfections. Each one is contributing to an overall degradation in your optics. So you've got all these surfaces, the front surface of the cornea, the back surface of the cornea, the lens. At each point, you can introduce some more problems. In fact, the lens can be all kinds of crazy things. It can be tilted off center. And the index of refraction of all these materials isn't uniform, for example. It varies across the location. And sometimes it varies in a nice, regular, symmetric way. And sometimes it varies in an asymmetric way. It's minerals. You sleep on your side, and you get more minerals on one side or the other or something. So all these things can go in there and modify it. So do we think those matter? Well, they matter for some people. Some people, they have pretty healthy retinas, and you put glasses on them, and you try, but they're not happy. They don't see any better. There's not an obvious reason, just from looking at their eye right away, why they don't see well. Other people, they see well in some conditions, but you change the light, and then they don't see very well. And finally, there are people who look pretty normal, but they see just exceptionally better than the rest of us, and that's an interesting case, too. Ideally, we could all see like that, or maybe we don't want to. That's a question for other people to answer. So my question is, how can we measure these aberrations? So everything I'm talking about here, everything that's an imperfection from the perfect optical system, I'm calling an aberration. And to measure this, we want to use, here's a few approaches that we could use, sort of direct measurement. We could take a holographic sensor and jam it in the back of someone's eyeball when they were looking at a point source of light and measure everything. That's objectionable for a couple of reasons. Here's a better solution, and in fact, something that people tried for a number of times. Instead of putting in all the rays at once, you could shine a small light in just part of the eye and then take a picture of where that spot got focused. You could repeat many, many times moving around and eventually build up a map of sort of where all those rays would end up. And this is time-consuming and error-prone, but in the 60s and 70s, they did this type of experimentation in a very limited way. So here's a better way. instead of sticking a sensor back there, just stick a light bulb. It's much smaller. And because the rays can be traced either way with general equivalence, let the light come out here and measure the aberrations out here where you can put a big sensor and it won't bother the person. And that's the approach that I was using and it's generally been adopted. So what we're really going to measure out there is the wavefront. Many of you are probably familiar with the idea of a wavefront. That's the wave definition, an imaginary surface joining all the points in space of a wave that have the same phase. That's, okay, it's a little confusing. I like the geometric interpretation better. If you think of all the rays coming out from some particular, here's a plane wave, there's a point source. The wavefront is just sort of an imaginary line which is perpendicular to all the rays at any point. So you could trace it anywhere and sort of by hand and imagine what that wavefront looks like. And that's what we want to find. That's a description. So we're going to take the eye. Rather than putting a light bulb in there, we're going to shine a small laser right down the top and make a bright spot in the back on the retina, just about where the fovea is, in fact. So people get nervous when you're talking about shooting a laser into the retina, and rightly so. It's something you want to do carefully with as little power as you can manage, and sort of the equipment that's out there all has a rating for how many seconds it's safe to put a person on there. We used infrared light so the person didn't see anything, but there's a thermal effect and it starts to warm up the retina. You don't want to keep them there for more than a few minutes. And in fact, we're able to do this all in a couple seconds.
Question. Are the aberrations similar for different colored light?
The aberrations are similar for different colored light. How about they are related but different? So yeah, and that's important. But it turns out that you can characterize everything by measuring in one frequency. So, and that's what's important going forward.
So far, you've shown this emanating from one point in the back of the eye. Do you actually scan over the back of the eye?
No, in this case, so you could do that, and then you would be essentially measuring the errors at different angles in peripheral vision. In fact, we have such sort of, the fovea, you have most of your important cones in one small place. And so for our purpose, what we were caring about is just down the center, the line of sight. And in fact, you could do that, and there's been some research into that. But your resolution is so low off axis that it's not as interesting. Oh, it's still interesting, but it's not what I did. And so this is what we were doing, was a single point. The light comes down, reflects back out, and so we can sort of imagine this wavefront coming out. At first, it's perfectly spherical. It's propagating out here. It hits their lens, picks up a bunch of funny spherical aberrations. It goes out of the lens. Most of the aberrations that it picked up coming in get canceled out by the other side, but not all. Comes up, hits the back surface of the cornea, hits the front surface of the cornea, and then it comes out here. So at this point, this is sort of the theoretical wavefront coming out of their eye, which contains all the information. Whatever was wrong with their eye at any point, we don't have to know where. This is sort of a description of everything that was wrong inside the eye. So this theoretical wavefront is out there. What do we do with it? Well, this is a technique that was originally developed for telescopes when you had aberrations. And the idea is just you sort of take a piece of, originally they used a piece of black paper, and you'd punch a few holes into it, and you put it close to your light source, and you crank the light source up so it's nice and bright. Little light gets projected through the holes, and you can put up some type of sensor. They used to use film. Now, of course, we're using a CCD or something related. And each one of those spots will make a little mark there. So if you were to look at the image that you would get, it would be something like this. You would have a hole for each spot, but it would be moved. And the amount of displacement would tell you something about the angle of that light. In fact, all you'd have to do, if I go back here, right, you can measure the distance from here to here by looking at your camera and knowing where it should be, and you can measure the distance from here to here by construction, and you can say, okay, the angle of that ray is theta and phi. And so because you know where the hole is, you've now characterized the position and the angle of each of those rays.
Does that tell you the phase?
Well, we're talking about the phase of the wavefront. It's not the phase of the, of an individual photon, the E field or something. So that doesn't tell you the phase directly, but you can infer it. position in the direction. Improvement, so that was called a Hartman screen, what was shown up there. Shack came along, and now it's called a Shack-Hartman or Hartman-Shack device, depending on which one you like more, and replaced a little tiny pinhole with an individual lens, so you're gathering a lot more light. That's important in our case, because to make our image bright enough, we have to crank up that laser that's blasting into their eye. We don't want to crank it up too much. So the more light we can gather, the better job we can do. So
in the original mask, the spacing was such to avoid aliasing with respect to the geometric optics, and then was the mask moved with multiple samples taken?
So on the telescope case, yeah, the mask was moved with, in fact, the original version was just a piece of paper with one hole, and you could trace it, and they decided it was better to make a little strip. You put it on the telescope, and you rotate it around every 10 degrees or something, and you could get a nice radial description of what was going on, which is well suited for the type of errors that you would have in a telescope lens. Really what I'm doing here is I am creating, in this case, a sequence of 9 individual cameras. I'm just using one CCD, but I've got 9 separate lenses, and I'm creating 9 separate images of this spot in the back of the retina. And in reality, I want to do this in 2 dimensions. So this is an example of the type of array that's used. This is one that's actually used in astronomy. The ones that we used in ophthalmology were smaller than that, about a third the size or so. In this case, 1,600 little tiny spherical arrays, and you could, lenses. You can just sort of barely see them in there. And it turns out to be quite a job constructing something like that. So they're fairly expensive, and they do it by taking a very thin sheet of, I think it's silica in this case, and they sort of engrave a bunch of cylinder lenses running down one side, and then cylinder lenses running the other side along on the other side. And so your net result is something approaching a lens if you make it thin enough, right, as the light goes through. So you put this all together, and it's called a Hartman-Shack sensor, and from it you can theoretically infer what's the shape of the wavefront that's coming out. So this is an example of kind of an image from a person's eye. You go in there and measure it. You can see a spot from each one of the cameras, and hidden somewhere in that positional information where the spot is information about the person's eye. There's a few other things in there too. This reflection here, what you're actually seeing is, or this kind of bright spot here, that's what they call the Purkinje reflex. We're putting in that laser near the center of the eye. Some of the light is bouncing right off of the normal portion of the cornea. So you can look and say, okay, this is actually the highest point in the cornea right there. So that's interesting. Some of these spots are nice and bright. Other of them have sort of some strange defects. You look up here, you don't have a nice spot. You have kind of a jumbled mess. And so you can look at the average and say where that is, but you can also tell that it's not a very flat wavefront. Just within that little spot, you've got something going on that's messing it up. So we want to take that. We want to correlate. So when you build your sensor, you're taking a normal picture of the eye, and you're taking this Hartman-Shack picture of the eye, and you want to calibrate it so you know where each of those spots corresponds to in terms of their actual optical eye. And that's going to be useful for later if you want to try to use that to correct their aberrations. You need to figure out where each one of those spots belongs. If you have a really highly aberrated eye, you'll see some strange patterns. The spots will be squished in one axis and elongated in the other, or you can have almost anything going on. And to do this properly, you have to know where each spot, you have to know which hole, or which lens corresponds to each spot. And so this is sort of interesting image analysis problem. You end up creating this graph that kind of compares adjacent spots and builds up a web which you think is the most likely characterization. Then you figure out which one is in the center by looking at the Purkinje reflex, and you go in and decide what the slope is for each one of those points. So now you have a surface which you've described, and there are a few more subtleties here. Right? You're measuring this some distance away from the eye, but you're actually interested in what the wave front is sort of right at the surface of the eye where it's important to them, or at some point inside. So you have to sort of back out how that wavefront would have changed from where it came out of their eye to where it measured. That's interesting information. There are a few ways to do it. Essentially, you've got a bunch of slopes and you want that you've measured, and you want to know what was the surface that created those. The obvious way is sort of direct integration. It doesn't work too well because of the noise in the system. There's a few other. Zernike decomposition is pretty popular. Many of you are probably familiar with the Zernike polynomials, a set of round basis functions that have been used in optics for a long time. More recently, we've started different methods. Fourier reconstruction works pretty well because if you're in Fourier space, going back and forth between a surface and its derivative is just as simple as doing a sine-cosine transform, so that's pretty easy. What do we expect those wavefronts to look like? So here's our sample nearsighted person. When we first described him, we had rays coming in and focusing in the wrong place. Now we're putting in light, and we are measuring the rays as they come out, right? And we expect something like that. So that's the kind of wavefront that a nearsighted person would probably have. And in fact, this is a measurement from a patient with about 2 diopters of nearsightedness. It's mild, just about the cusp of when you would need to have glasses. Most people with 1.5 diopters don't bother wearing glasses. Most people with 2 do. So it's just about like we'd expect. Now here's a couple more interesting cases that are not quite like we'd expect. These are 2 more people who both have about 2 diopters of myopia too. So all 3 of these people are essentially wearing the same glasses. But in this case, there's a significant amount of positive spherical aberration on the left. The patient on the right has a significant amount of negative spherical aberration. So you can see, even though the same glass is the best fit for each of them, they're going to have a substantially different viewing experience wearing those. Here's a few more funny ones or interesting ones. This is just sort of pure spherical aberration with a few ripples. There's kind of a phase map on the left and then a 3D interpretation of it on the right. So this is someone who didn't like glasses at all. They didn't find any glasses that helped them. But especially at nighttime, they had poor vision. And you can sort of imagine why that is. If the pupil was stopped up nice and small, it's relatively flat in here. But when they have the whole shape in there, some of those rays are going to be focusing one direction, some are going to be focusing the other. Here's a patient with what's called mixed astigmatism. So there's actually an average, sort of a saddle shape, an average trend. He's slightly hyperopic along this direction and slightly myopic along that direction. And in looking at the wavefront, it's tempting to imagine that that's kind of the shape that's wrong with their cornea. And in some cases it is. But in most of the cases, it's a combination of things at different surfaces. So we are measuring all the optical aberrations in a person's eye. What can we do with that? And one of the things that I'm going to be talking about now is using that to understand how they see the world. A couple of things: we could maybe estimate how well they see in a way that's more meaningful than putting up a letter chart and asking them to read. And we can kind of understand if they have things that they're complaining about, things they don't like. It can give us a sense of what they really look like and help us determine maybe how to fix it. So the basics here is using a point spread function, which is almost a reverse of the measurement we took in the beginning, but we couldn't actually measure their point spread function. So we're sort of inferring it from all this information. Right? The idea is a person is looking at a small point of light, it interacts with their eye, and it generates some image on their retina. Here are some real simple cases. A person who's nearsighted sees kind of a fuzzy blob. A person with astigmatism, right? So that's nearsighted on one axis. This other axis, it's a fairly well-focused mark, but along here you have significant blurring. So if there are lines that are running this way, it looks pretty sharp in focus to them. But a line running this way will not be in focus. Here's our emmetrope again. This guy sees pretty well. Now even he doesn't need glasses, has good vision. There are some ripples, and you can see some of the effects down there, but they're small. So, but this is a pretty limited set, what I've shown you so far. What I really want to do is realistically perceive how a person would see something. So I got a bunch of smart people in the room who knew about eyes, and I had them kind of tell me everything they thought affected how a person sees, from optics and physiology, and then everything that I was sort of able to characterize, I threw into a model, the idea being that maybe we can actually predict what people see. So the approach is a geometric model. This is a graph that kind of puts together a few elements. Here is an actual wavefront that was measured. Now, I used a 6-surface version of the eye. Here I'm just kind of showing a simple 1 surface. You got rays coming in, they're affected by the wavefront, and they come down in focus. And in fact, these are real rays from a real patient. I've magnified the scale by about 10x to make it bigger. but you capture the light from all the points, you put it through all the physics that you can, and sum it all together, and you end up with a point spread function sort of predicting how that person would see something. Here's some simple examples, and I'm starting with just one wavelength. For a sense of scale, scale is tricky when you're talking about this because it's not that intuitive. So in many cases, I will throw on a letter E onto these graphs, and that's basically a resolution indication of the 20/20 on an eye chart. So roughly, this is 5 minutes of arc on most of these graphs. And so if the features of your point spread function are small compared to the E, then you can see better than 20/20. If the features are large compared to the E, then you cannot see 20/20. So a person who cannot see 20/20 and a person who can. That's just one wavelength. Of course, an important part of our visual experience is that we're seeing in white light. Now, just to back up a little bit and to answer your question, we measured it in the infrared, and now we're talking about something in the visible spectrum. So you have to go in and figure out how would those, we measured it one way. Oh, is that your question? Oh. And what would it look like in a different wavelength? And that's not too hard if you understand what the dispersion formula is for all those surfaces. And so that's part of what's going on here. So chromatic aberration, if you're looking at white light, your eye focuses the blue part differently from the red part, from the green part. And it turns out to be a significant effect, over a diopter in the range that we really care about. Here's red light kind of modeled in a myopic eye. It's coming to that focus soon. If we were to put in the same light with blue, we would get this, right? So he becomes actually a little more nearsighted when we put in the blue light. So there's one wavelength. So add a whole series of wavelengths weighted proportionally over the white light spectrum kind of that we care about. So it fills it out, doesn't change it too much in these cases. But we can do a little bit better than that because we can go in and we can model the visual response to those wavelengths, and we can come up with a color version of it. So now, assuming that the person's looking at a white source of light, we're making some predictions about what they're going to see in color. This is a diffraction limited case, a color airy disk, if you will. And here's our mixed astigmatism patient again. It's interesting. You can see the blue light is better focused in one direction, and the red light is better focused in the other. These are two eyes that have roughly the same amount of defocus, except one of them is nearsighted, and one of them is defocused in the other direction, the farsighted. And you see kind of a shocking fringing effect going on. And it turns out that is a real observed effect. It's just sort of on the edge of human perception. But it is real. If you look at our nearsighted patient again, that was the blue light we talked about, that was the red. You put them both together and you get something like this. And in fact, this is sort of what we see. Our nearsighted patient is imaging after the point of best focus, and so he has kind of a blue fringe on the outside. Our farsighted patient is imaging before the point of best focus, and so he has something like that on there. Of course, the eye doesn't respond to light in a linear fashion, so that becomes important in a way that's useful in dark conditions, but it's actually irritating when you've got aberrations because light that otherwise wouldn't matter too much starts to show up and bother you. So in fact, if light gets too bright, it begins to saturate the receptors, and so you have to decide how bright do you want that light to be. It's not just kind of a theoretical point. You have to put some actual value to it and then proceed from there. How you do the reconstruction seems to matter. In the beginning, we were using Zernike polynomials, which are relatively smooth and well-behaved and had historical reasons. But they don't capture all the information that we use to measure. And so we experimented with a higher resolution reconstruction, essentially using all the points in a more realistic way. And this is the sort of type of output you get. And this turns out to be pretty close to what people actually see. If you are slightly nearsighted or farsighted, and you look up at a street lamp, for example, at night without your glasses, you'll see something like that. It's fuzzed out, but there's a fair bit of texture hidden inside there.
Well, it seems like the basis functions you really want to be kind of wavelets that corresponded to the standard geometric aberrations in the eye, as opposed to a pure smooth function.
Well, but what are the standard?
Well, I don't know.
Yeah.
But you'd have to measure them at high resolution and then back project and come up with an orthogonal set of basis functions to represent them.
And so that's what the Zernike functions were originally in the telescope days. And in fact, they would only use something like 8 or 10 separate functions, and that would do a pretty good job of describing telescopes.
But they were for telescope
Right.
spherical lenses.
Exactly.
As opposed to the
Exactly. The human eye, people tend to have stories like they were out playing and their brother threw a rock and it hit their eye, and ever since then they've seen funny things, at night. And so then obviously they've got some kind of chip or scrape on their cornea, and that's something that's not necessarily well defined by a smooth basis function. And that's a field of study. The bottom line is it seems to be that we want to use as much information that we can. The first attempts didn't capture everything. Here's our patient with the high spherical aberration. See, that looks pretty similar when we used the higher resolution reconstruction. But here's someone who had significant problems, and there you're getting entirely a different effect. This person was complaining about double images when they looked at things, and you can't see that here. But you can get a sense that, yeah, they might get two sort of distinct images when they looked at something there.
How much would that be affected by changing the spatial resolution in the lens array that you used for the capture? Just synthetically averaging it down, say, a factor of 2 in each dimension and then going through. I'm just wondering if you captured the data with enough fidelity or whether there's almost like a Gibbs phenomena in the sampling.
That's a good question, and the way you do that is by increasing the resolution until you don't see changes anymore. And I didn't, yeah.
Decreasing the resolution of what you've got and
Right.
seeing whether
So, and the answer is when you decrease the resolution by a factor of 2, you see, in most cases, you see small changes that aren't very significant, but there are some cases where you do see. And so there's probably, as you make it higher, there's a smaller and smaller percentage of the population for which it matters. And I don't know exactly what that is here. We're getting close. In fact, since I've stopped working on this, they've gone in and doubled the resolution. I don't have that information yet about how that's working, but obviously it's a drive. They want to do that. This is sort of a repeatability test. A number of people were tested several times throughout the day. And so what you see, minor changes due to accommodation. Your eyes get tired over the day. You blink a lot. Your eyes get dry. You have something to drink. All those things change your optics a little bit, but they don't change it too much. They're unique enough that, with 50 different people, you could probably identify someone by their point spread function. So that's the theory. Does it work? And the answer is that it seems to. This is a patient who came in complaining about poor vision. Specifically, they had artifacts. They had things they were seeing that they didn't like. And it was kind of hard for them to describe what they saw. So they were given a small piece of paper, and we set up a target, a little white light in front of a grid, and they were asked to close one eye, then the other, and draw what they saw. Then we took them, we measured them, and we did this point spread function prediction. And this is what we got. So it's not perfect, but it's a pretty darn good match. It's probably within the limits of the artistic ability of the patient, which is probably more artistic ability than I would have. So it seems to. This is a long way from a study on 1,000 people where you might try to go in and really prove it, but it looks very promising. So it seems a little voyeuristic to me. You're going in and you're saying, okay, what does this person see? You're putting yourself a little bit in their head. And so that's interesting in a way. You get a sense of how they perceive the world in a way that we really haven't been able to do before. And so one of the things that's hard in grappling here with is the sense of scale. This is someone with bad vision, not terrible. There's probably people in the room with worse vision than this. And here's someone with good vision, a little tiny bit of sphere and cylinder and some of those higher order aberrations. I've got the E in each of them, but if I put them on the same scale, you really get a sense of what life is like. This person has pretty good vision. Person here, not so much. In fact, you imagine if that's what you're used to, navigating the world with, this is just phenomenally bad. Another sense of scale that I find works pretty well. The full moon is about 30 arc minutes, so you can throw it up there. So Mr. Good Vision can look up and see the moon, count the mare on the surface, whatever, see it pretty well. Mr. Bad Vision, he can tell there's a moon there because there's a fair amount of light, but it's spread out over a significant portion of the eye. And in fact, if you threw up a flashlight, he might think that was the moon too.
Is that really saying that you can see a point of light as being bigger than the moon?
Yeah, yes. It's pretty bad. And people get, before they become, pathological cases, you'll have people that are 2 or 3 times worse than that in terms of and the whole spread out. This is probably about a 90, 95, 97th percentile of bad case. And over here, the good case, that is better than your average person. I mean, that's, so we're doing this, we're predicting what people are seeing. Here's some of the fun things that we can do with it. One of them is image convolution, which you've talked about before. You have a point spread function. You can apply it to a surface and imagine, okay, well, how is someone going to see with that? So we have color at our disposal. So we can go in, take an object, and analyze it from a color point of view and predict what is that person seeing, in this case, under white light. So here's our 20/20 eye chart. And at first glance, you might say, well, it doesn't look very sharp and focused. But this is the 20/20 line. When you're reading the 20/20 line, the only test is, can you tell what those letters are? And there's obviously enough spatial information. You can go through and read those letters. And you can probably go through and get some of the letters off the next line. So this person has vision that's better than 20/20, or at least I can make a pretty strong prediction about what their visual acuity would be, according to the Snellen test anyway, just by doing this. But that sort of raises the question, what kind of light are we interested in? Well, we have some choice. Here's a patient with good vision. In this case, we've given them a solar spectrum and calculated what the eye chart would look like to them. I think the 20/20 line is here. So this person has great vision when you're in white light. Now, if we were to go in, let's say they were looking at the eye chart, all they had was a little blue LED flashlight. They turn that on, they still see pretty well. Now they're looking at just one wavelength. Now, instead of a blue one, if we were to give them a red LED flashlight, this is what they're seeing. Same eye chart, but because the aberrations are affected by the wavelength, they're getting a substantially different image. In fact, now because it's so spread out, they're getting a few points. They get these kind of double images that people hate. This is the spectrum under a sodium streetlight, which is mostly 590 with a few spikes around there. And so this person might be really happy, and you may have noticed this yourself, might be really happy reading a newspaper in fairly white light, but you get into a limited spectrum, you try reading it, all of a sudden it's hard to focus, it doesn't seem clear. And it turns out this is, you actually use these chromatic aberrations, at least this is what we think. You use these chromatic aberrations to help as a focusing visual cue. The eye isn't as a camera, you're trying to focus it just like a normal camera, but you can't do these fancy splitting the optics and recombined. And so your eye is always looking for information. Will I improve the image by focusing out, focusing in? And because blue light's a little more tightly focused than red, that's one of the cues your system uses. Which of those two is in better focus, it'll move it in that direction. So if you have a white light spectrum which is continuous, you have a nice gradient, your eye is sort of trained to use that to help you focus. If you're looking at an artificial white light spectrum, so some of the compact fluorescents, if you look at the spectrum, they basically just have a few big lines and most of their energy is there. And you can say it has a certain color temperature and it's approximating a certain spectrum. But it's not really, when you go in and look at their point spread function, instead of giving them kind of a nice averaged effect, you're getting 3 sharp, distinct effects that are all focused differently. And this is probably one of the reasons why some people with maybe eyes that are a little messed up don't mind it too much, but people who have good vision or people who can correct well with their glasses, so they have good vision, they tend to not like the compact fluorescent lights, or some of them. That's probably one of the reasons, because their eye is confused about these cues. It's got multiple images, it's trying to decide which one to focus on, and it gives you a headache. So some of the newer lights have a more broad spectrum, and that'll obviously be the direction we need to go in to make people happy with. We don't have to limit ourselves to little targets like that. We can go in and simulate things in the real world. This is a person with the person who should be wearing their glasses to drive, just barely, but didn't bring them. These are the headlights from a BMW at 100 meters away. In this case, we can also model the light source. So those are the halogen lights. If the driver had instead opted for the xenon, we can go in, and that's what the person would see. So we have this ability to kind of recreate high dynamic situations and say, what would this mean to the person? What would it look like? Everything I've shown you so far has been 2-dimensional, but the model of the eye that we've got is 3-dimensional, and there's some extra information in there that's useful. So I'm going to start with as a patient who sees pretty well. This is their point spread function, just sort of as they are, 0 diopters. You don't put any lens in front of them. If you were to artificially, there's an E for scale. If you were to artificially put a lens in front of them and make them far-sighted a little bit, they would have this kind of far-sighted point spread function. You could also put a lens in front of them to make them nearsighted, and you'd have this sort of blue fringe nearsighted point spread function. So dioptric power is one way to think about the difference between these, but you could also imagine them as being before and after the imaging plane, because as you move forward and backward from the imaging plane, the power changes. So you can sort of establish them in 3 dimensions in some sense. Then you can go in and fill in the intervening points and create a description sort of the volume of light as it's coming down to the best focus and as it's going back out. So that's what we call volumetric point spread function. There's a variety of ways of calculating these, but here we're taking all the information we have in the model and really trying to understand this is the light. Well, in fact, it's coming in from that direction, coming down to the best focus. And if we could see the light as it was coming into their eye, that is more or less what it would look like. And in fact, surprise, surprise, it looks kind of like this model we had there. Now this is a volumetric point spread function for a simple aberration-free eye, completely flat. And it doesn't seem that interesting until you put it next to this. This is the same thing for an eye with a single wavelength of light. So this person who's looking at the single wavelength of light, or alternatively, who didn't have any chromatic aberration, he has a really nice focus at one point right there. But as soon as he gets a little bit before or after that, the focus just goes to heck really quickly. So over here, because you've got all these frequencies of light, and they're all focused slightly different, so you actually have a nice compact point, probably that's useful for seeing and reading over almost 5 of these. So the fact that we have these chromatic aberrations gives us an improved depth of field. You can pick up features much more easily. That's another one of the reasons that people really like polychromatic light. Here's our mixed astigmatism patient. So you'll see better focus on one axis out here, better focus in the other out there. No point where everything comes in. But with the right combination of cylinder lenses, you can do a pretty good job of correcting that person. Here's someone who has no hope of being corrected. You could put glasses in front of them all day and try changing the focus or changing the cylinder. But there's no point along there where you have a nice image. And so this is the type of person who's really complaining and unhappy with what they're seeing. At different pupil sizes. So obviously, when people have small pupils, they've got, so this one is sort of unfair because you've got diffraction effects that I've been ignoring. And down in the 1 millimeter, 1.5 millimeter range, they'll start to show up and decrease the quality. But up at 2 or 3, this is where people see pretty well. And also, they have a pretty good depth of field. You get nighttime conditions, 6, 7 millimeters is common. The point spread function is not nearly as good. And if you get off a little bit, it gets worse.
Are you able to compute that from one measurement, or do you actually?
From one measurement.
So you don't actually have them change pupil size by changing ambient light?
You measure them at the max. You measure them in a dark room. And because you're able to tell which part of the system the aberrations are associated with, you can figure out how it's going to change as the pupil size constricts down.
There's no other geometric effect with change in pupil size, or it's minor?
There are very small effects, so, and that's something that probably would be worth including. I didn't, but it's a good question. One thing that people tried with early was there's little drops of atropine you can put in a person, and it paralyzes the muscles in the eye, and your pupils get very big, and you look like you're on drugs. And it turns out that changes the wavefront of the eye, because you've got kind of tension all the time in these muscles in your eye, and when you paralyze those, all of a sudden, that tension goes away. And so that turns out to be a bad way to measure people, but give them a few minutes in the dark room seems to be best. Everything I showed was for daytime conditions. Using the same aberrations, you can model nighttime conditions where you've got a different diameter, different to the pupil, different peak response. So here's the same patient in both conditions. Obviously, it's a little worse on the right, but sort of the interesting thing here, in the daytime, if you look, their best focus is just about here at the retinal plane, and they can see pretty well. At the nighttime, because they're most sensitive to different wavelengths that are focused differently, and because they have different aberrations in the periphery of their eye, which are only available when the pupil's open, their best focus is actually up here a little bit. So this person, I'm guessing, has what you call nighttime myopia, which is a fairly common condition in which people see okay during the day, but they find they need some weak glasses at night. So if you can go in and measure them, can you correct them? So I'll go through this real fast. People have been trying to correct vision for a long time. Rumor has it that Nero had an emerald monocle that he would wear to help with his myopia. It's probably not true, but it's a good story. The first definite spectacles came out of Italy, ground quartz. Benjamin Franklin, so things stayed the same for a long time. Bifocals, astigmatism, you guys are familiar with Airy from his work. He had astigmatism himself, and so he sort of invented a cure for astigmatism just personally, created the first cylinder lenses and used them himself, and then went on to promote the idea. Contact lenses, in fact, have been around for over 100 years. The early ones were made out of glass. You can imagine some of the perils of wearing that. The idea of modifying the eye permanently to make it see better is a compelling one, and sort of the first effort was this doctor in Colombia, and his plan was cut the cornea off with a knife, freeze it, turn it on a wood lathe to change the shape, and then sew it back on. And they didn't try that very long, but they learned some interesting things. One is that actually sometimes it worked, and two is that the eye is amazingly, it does a good job of healing itself, and once you put something on there and it stays for a few months, it's pretty stable. So some people actually came away from that with good vision. But it didn't work that well. Radial keratotomy, the idea, well, it was discovered by accident. So this doctor in Russia, he had a patient, got some broken glass in his eye. Maybe he was wearing a contact, I don't know. He had to go in there and remove all this glass. In the process, he had to put a bunch of cuts into the cornea to get the glass out. 6 months later, he came back and checked on the boy, and the boy didn't need to wear his glasses anymore. So he thought, brilliant, all I have to do is put some cuts in the eyeball and people will see better. And to a certain extent, it works. The eye is under sort of dynamic tension at all times. So if you make a cut somewhere, every other piece of the eye will change shape a little bit. And he came up with some formulas about how to cut and how many. And being in Russia, it was sort of picked up by the government, and they made these incredible assembly lines. It's hard to see here, but there are 8 patients on a big rotating circle with 8 beds, and there are 8 doctors. And each doctor makes one cut that he's especially trained for, and then the beds rotate. That's what you can see happening, and they do the next cut. And this was better than the freezing, but it was picked up a few other countries a little bit. So there are people, and in fact, some of the early patients we saw who were complaining about problems that had this procedure done decades ago. And some of them see pretty well, and some of them have problems. Again, we learned a few more things. Sort of, it probably because it was happening in Russia and it was set up so big and it was pushed by the government, it went on for a number of decades before they finally admitted that it really was not a good thing to do, and they shut down the process. There's still plenty of people who had that procedure. Excimer laser came along in the 80s originally for semiconductor use. They discovered this is a human hair. They discovered you could make really fine incisions with it, remove tissue pretty cleanly. And so Dr. Steve Trokel in the 90s applied it to laser eye surgery. The idea was you want to change the shape of a person's lens. Each time you shoot the laser, it takes off a little layer of material. So you can do a treatment that looks something like this, making it beam smaller and smaller. And when you're done, you end up with something that looks like a lens. And so you etch that onto the person's cornea, and it changes their focus, and then they see better. And it took some iterations, but in fact, it works pretty well. But what we want to do is sort of a whole level beyond that. These are the simple shapes. These are the kind of shapes we want to correct. You can't get there by just describing this series of concentric wedding cake layers. One of the interesting challenges here is that when we're measuring that wavefront, we found that if you want to correct it, you need to do it accurately. And sort of our goal here, you want to get an accuracy of better than 1/10 of a micron of tissue. And each laser pulse removes almost 3 times that much. So you want to find a way to put these laser pulses together that gives you an accuracy and a precision much smaller than a single laser pulse. So it becomes an interesting problem. Other problems, it's not really simple what happens when the laser hits the eye. The second pulse, the first laser pulse doesn't change the eye very much. It excites the tissue in some way. The second laser pulse removes some tissue. The third one does it in a different way. So it's sort of nonlinear projection effects. If you put a laser pulse down in the center of the eye, it's hitting a different shape than near the edge. So you got to take that into account. And we talked about the structural changes with PRK. As you're removing tissue, the eye itself is going to change shape as it relaxes. And so you need to take that into account. And so what we did was do lots and lots of measurements and build a model that predicts for a given series of laser pulses what's going to happen. We're not yet answering the question, what laser pulses do? We just build the model. And a lot of this was done with pig eyes. That was the summer intern's job, was going in and cleaning these and setting them up. And we do lots of experiments, shooting them with the laser in different ways and measuring what happened. And then we had to do some experiments to figure out what are the differences between pigs and humans, and so on and so forth. Essentially, then we're reduced to a sort of a puzzle. You've got these pieces, which are the laser pulses, and you know the final shape you want, and you've got to find a way to put them together that gives you that output. Except in this case, the pieces here are all the things the laser can do. And the final shape we want to get is what the wavefront change we want to induce on the eye, including all the structural changes and everything that goes on. And in fact, the way we do that is we use the model as a, come back. We use the model and do a global search on it. So we start with a random treatment of pulses and see how well does that correct the eye. We go in and we modify it. We use kind of an iterative stochastic evolutionary strategy. So we make little changes to the treatment, and basically you optimize the heck out of this model so you can evaluate about 1,000 different treatments per second. And then you just let it run. It takes about 45 seconds per eye and current, and it improves. What you saw here was the treatment plan we wanted to achieve. This is the best solution so far as it's doing its evolutionary search, and there's the difference between the two. So there's no way to directly solve the problem, but if you do your search, you can find out if there is a solution that's good enough. These are sort of the details. There's for that one you saw there. It turns out you're doing this one with only 113 pulses. That's roughly the size and location of the different pulses. If you go in and model how each one alters the cornea and how they interact, you can see after a few, they start interacting in a very complicated, ugly way. But the purple dots there indicate the shape we were trying to get. So just sort of by magic, when you stack them all up, they come out to be what you want. It's not by magic, of course. It's because we searched through thousands and thousands of possible solutions. So the question isn't, how do we find the right solution? The question, is there a solution that would correct this person? Real quickly, so some of the challenges. You want to do the surgery, the eyeball is always moving, even during the surgery. And you have to make sure you put each pulse in exactly the right place. This is not a real eye, but it's motion of a real eye from one of our experiments. And so the way you deal with that is you have cameras that are watching the eye, and as it moves during the treatment, you re-aim the laser between each pulse so that it goes down in the right place. Some of that motion is associated with the heartbeat or the breathing, and some of it is people just nervously looking left and right, even though they're not supposed to. Torsion of the eye. Most people don't realize it, but your eye can actually twist quite a bit left or right without it bothering you too much. In fact, I could go in and probably rotate your eyeball 10 or 15 degrees, and it wouldn't hurt you too much, except for the grabbing your eyeball part. Right? You've got muscles on the top and bottom that steer it, but there's no mechanism to set it like this. So if you're looking at somewhere, and then you look to the left, and then look up and look down, there's sort of a hysteresis. Your eyeball's at a different angle now. And so that matters to us if we're measuring these little aberrations. And this is another visualization of what would happen if you tried to correct those errors and you got the angle wrong. So all right, pretty good sharp focus, nice point spread function when everything's aligned. If you measure them one angle and you treat them off. So real eyes usually only change a few degrees, 4 or 5, but they can change as many as 15, which is what I'm showing here. So you need to get that right. In fact, what we do, that initial picture of the eye I told you about, we go in and we look at features on the iris, and then when it's time to do the surgery, we look at those same features and we rotate the whole treatment to line up on that eye again. The laser is pretty safe and it's not too hot, but you want to give the treatment as quickly as you can. So, in fact, eyeballs actually melt if you're not careful. They don't call it melting, they call it denaturing. And if you heat up the eyeball, it actually starts to change shape, almost like a plastic bag. If you put a blowtorch on it, it'll curl and wiggle. So every treatment we go through, we analyze it from a thermal point of view and say, okay, what's the temperature? Then we rearrange the pulses and change the timing in such a way that we'll stay at a safe treatment temperature, but get it done as quickly as possible. So we put it out there, and in fact, it works pretty well. This is results from a study. Everybody could pass the driving test. 98% were at 20/20. And if this is what we were really interested in. 70% got to the 2016 or better point without glasses or contacts. And that's really kind of the amazing result. We're taking a fairly big group of people and moving them into the better than normal category, which was our goal. And that's an example of the point spread function from one of the patients before and afterwards. So that's it. That's the eyeballs are cool, and there's lots of new technology you can use to go in there and study them, and lots of opportunities. So thank you. It's a little late, but any questions?
So did you do any standard optical correction, not laser ablation, but rather just with, you know, prismatic lenses and one thing and another in your initial tests to see how predictive PSF was?
Yeah, here's an interesting, one of the things we could do is instead of actually, so we had the model that described how the laser interacted with the cornea. We were able to sort of replace that with a model that described how the laser interacts with optical grade plastic. And so you could take a patient whose vision was something like this, and we could go in and take a lens, and we could calculate what was the wavefront we would have to do to pre-warp the light so that by the time it got to their eye, it would neutralize the aberrations that they already had. And so that was one of the safety things we were able to do. Try this for each patient, give them a lens, have them put on, look at an eye chart, and see, were they happy? It's sort of tricky to do this because you've got these little aberrations. It has to be very carefully aligned. You know, with glasses, it doesn't matter too much. But if you're 2 millimeters off here, all of a sudden, you could be making the problem worse instead of better. So it's not a good solution. You wouldn't want to walk around with these in life. Although for years, I carried one of these in my wallet as kind of an emergency monocle, and it worked okay. But so that was one of the things. There were also some experiments that I wasn't a part of to use adaptive optics to kind of in real time have a deformable mirror that would measure and change these so people could look around and see what they were looking at. It never really turned into a product, though.
What company is this, and where can you get it done?
Oh, I need to be clear. I'm not advocating anything. The company that I worked for was called Visex. In fact, they were bought up by a bigger company called Advanced Medical Optics, and the procedure has FDA approval now for a fairly good group, but not everybody. People who are real extreme vision one way or the other aren't yet approved. It's still early experimental, but it's increasing. Most of the laser eye surgeries done in the US in the last 6 months have been with this type of technology. The doctors like it because they charge more. The company likes it because they can charge more. And the patients actually end up seeing better. So it's pretty much win-win. But I'm not advocating at all for anything. This is just interesting work.
Thanks.
All right, thank you.